the integral from 1 over x squared sine 1 over x dx. So I'm trying to teach you the basics. Nothing's really sophisticated. So when I look at this function, this is the function 1 over x squared sine 1 over x. I would rather have just sine x or sine y or sine t, but not sine 1 over x. So this is an outer function, this is an inner function. So if I could get rid of 1 over x, then, I could simplify a little bit, right? So let's say, let u be 1 over x, as long as du is in the problem, or it's easy to make up. I can make up a number. I cannot make up x cubed, right? So how will I continue then? Right, but remember?
Yes.
Yes, please, please. So here's what I see in the integral. I see the 1 over x squared. I see the dx, but it's not enough because du has 3 pieces. I have this piece, I have this piece, but I don't have this piece. That's easy to make up. I'll multiply by -1 twice. Multiplying by -1 twice does not change anything. But now I have all 3 pieces that go into du. I have 1, 2, 3. So there is a minus outside, and then what? The integral from I have to change this. This is left over. Sine u times, that's it. And this is way more human than the first one, right? The initial, the original one. So then what do we get? I'm asking myself now, I shouldn't write this just yet. So I'm asking myself which function is sine u or negative sine u? But positive, right? Because there is a negative in here. Yes, it doesn't matter.
Oh, it's still.
Yes. You can, yes, it will cancel out anyway, so you can keep it if you like. Actually, it's the same thing. So you can keep it if you like, but it will still cancel out. Since this is an indefinite integral, it's a family of functions. Infinitely many functions have the same derivative, but I have to go back and take the substitution, meaning I have to replace u by 1 over x. So this is cosine 1 over x plus a constant c. In case you have doubts, all you have to do is differentiate this. Let's not look at anything. How can you give this to Eric? So let's not look at anything and just differentiate this. When I differentiate cosine, I get negative sine 1 over x times the inner function prime, which is -1 over x squared. I differentiate c, I get 0. And when I multiply these two, I get this, the original function. So I know the answer is correct. And I can do this only because it's an indefinite integral. But if it were a definite, I could have not done this. Because if I differentiate a number, I get 0. I will never get the function that I started with. Is this better? Yes, no?
Have you ever run into like having an integral from a to b and then you use your substitution? Like on a test or anything?
It's the same thing.
Yeah, but like would you recommend to keep it in you when you take it and then you have to do f of b minus f of a, or would you rather us change it back and plug back in since it would be like the same thing, you just have to change the point?
Yeah, that's what I was saying. I recommend when you, let's choose definite integrals now. When you determine a definite integral, do not go back. Because first of all, you cannot write it in u without changing the limits of integration anyway. So the limits of integration, let's say, are between 0 and 1 for x. You cannot copy them for u. That would be incorrect. So what's the point in going back? So you are changing the integral from a complicated situation into a simple one with new limits of integration. Why would you go back? to the complicated one. You don't want that. So you want to stick with the simple one, the answer will still be a number. If you use x, or if you use y, or the substitution, you will still get the same number. Why go back? But with this, I have no choice.
Yeah.
Because I have to present the answer in the variable that was presented in. Good, so let's choose definite integrals now, or whatever else you want. Yes. Yes.
With this one, do we just go from 0 to 3 because they're opposite?
So, very good question. If the function, first of all, every time we determine a definite integral, what is the first thought? Continuous on the interval, that's the first thought. What is the second thought when I see a symmetric interval? Is it odd or even? If it's even, then I'll say twice the integral from blah blah to 3, from 0 to 3, right? Now if the function is odd, I would write 0. So the integral from -3 to 3, from 2x to the 4th plus x squared dx. Since the function is even, how do I know? Well, plug in -x, you will get the same thing with f of x. Nothing will change. If you replace x by -x, nothing will change, so the function is even. And the interval is symmetric. And also symmetric interval. Yes, I would write twice the integral from 0 to 3 from 2x to the 4th plus x squared dx. Do I have to? No. It's easier. Because after I find the antiderivative, it's always easy to plug in 0 than -3. And since the answer is the same, why not? So
So it went to 0 because it's a negative number?
careful, let's take a look. Let me refresh your memory on this. The function can be odd or even, and the interval is symmetric. So let's take a look. So here is an odd function. We know this function is x cubed, but we don't care, it's just odd. And we want to determine the integral between -a to a. So the integral from -a to a from f of x dx. And this would be the integral. Since the function is odd and the interval is symmetric, what is the answer?
0.
Yes, because this area is positive, this area is negative, and they're equal. So the answer is indeed 0. Let's see what happens with an even interval, with a symmetric interval for an even function. This is an even function. And here's the interval between -a to a, and this is the area. What is the integral from, what does it equal to from f of x dx when the function is even? Two identical pieces, but this time they're two positive identical pieces. So that's why we are allowed to change it into twice the integral from 0 to a from f of x dx, which is easier to calculate than the integral from -3 to 3. Is that better?
Okay.
Is that clear?
Yep.
Okay, so that's why we wrote this. Do we have to? No, but it's easier to calculate. Okay, so then we continue. Two outside. 2x to the 5th over 5 plus x cubed over 3 from 0 to 3, which is easier to calculate. We only need to plug in 3. So 2 to a 5th, 3 to the 5th, plus 27 over 3, which is 9. So 3 to the 4th is 81. 81 times 3 is 243 times 2 is 486. Thank you. Plus 45 over 5.
Is that 2 over 5 times 3 to the 5th?
No, I have to perform this and then find the least common denominator and multiply this by 5.
Okay.
So I only multiplied this by 2 and then found the least common denominator. So this is 2 times, I got 531 over 5. Correct me if I'm wrong, 1062 over 5. Any questions? Is this okay? Good. Anything else you would like to look at? What about f? Is the function continuous? Yes. Cosine is continuous everywhere. And tangent is continuous between negative pi and pi, or negative pi over 6 and pi over 6. It's not continuous at negative pi over 2 and pi over 2, but it's continuous everywhere else. Okay. So I check that it's continuous. Now I see that the interval is symmetric. And I would like to check whether the function is odd or even. What do you think? Yes. Every time I see tangent, not tangent squared. Every time I see tangent, and this is even, I see tangent by itself times an even function. This answer, the function is always odd. Since it's an odd function, I will have to write that this is 0, and I have to write y. Symmetric interval, odd function. Good.
And if you don't catch that, it's still like would result as 0.
Yes. Yes. Absolutely. Yes.
Are there like anything we can memorize to see whether it's odd or even? Like,
Yes. One thing that I can say is that when it comes to trig functions, is that your question?
Yeah.
Yes. For trig functions, everything is odd except cosine and secant. These are the only functions that, so these are even. The only functions that have only cosine in them.
Is the ones that are even?
Everything else is odd.
Everything else?
Sine, tangent, cotangent, cosecant.
Gotcha.
Sine, cotangent, cosecant, and tangent. Basically, all you have to remember is that cosine is even. And then which other function is? Even the secant, because secant only has cosine in it.
And obviously, if one of those are squared, it would be positive. Because
Yes.
it's squared.
Yes, if you square these, they will become even. Yes. Right? Because this is x cubed.
Right.
If I square x cubed, I get x to the 6th, which is even.
Even.
Right. So this is tangent. But if I square tangent, I get tangent squared, which becomes even. Very good. Okay. Next question.
How about number 8?
Number 8. Yes, very good. With number 8, we have a function given in the form of an integral from natural log x to 2x squared sine squared t dt. This is a function. We're not asked to find the integral. We are asked to find the function's derivative. So we are asked to find f prime of x. But this is not ready for differentiation. So what do I have to do first? Yes, break it up into two pieces. Very good. The integral from natural log to whatever plus the integral from that whatever to 2x squared sine squared t dt sine squared t dt.
Did you flip it?
Yes, I have to flip the first one because it's not ready for differentiation. Excellent. Fundamental theorem of calculus requires that the lower limit is a number.
Which makes it negative.
Yes, when we flip the limits of integration, you did mark your calendars for the final exam, correct?
10?
The final exam, right? In 3 weeks, 2 weeks from Tuesday. Okay. Now we're ready to differentiate. So please tell me what to write. So remember, we are differentiating an integral. When we differentiate an integral, the symbol goes away and dt goes away. Nothing changes here, except we replace t by this. Sine squared of natural log x times, careful, we are not differentiating the function, times 1 over x, plus times, that's it. So this procedure only shows that differentiation and integration are inverse operations, nothing else. We are given a function in the form of an integral and we are differentiating it, but since it has an integral in it, when we differentiate an integral, the integral goes away and we get back to the plain function. Not that plain, you would say, because I have to plug in natural log in it. Good.
So that would be the
Final answer. If you want, you can rearrange it a little bit, put 1 over x in front and put 4x in front of sine squared, but no one can do anything else to it. We're not even supposed to, even if we could. Yeah, we can't. Next question. What I would like to show is number 5 before you choose anything else. There are certain situations, like this one, in which you cannot determine the antiderivative. But we can still come up with a number, an approximate number, or an approximate area, I should say. So this is the integral from 0 to 16 from e raised to x squared dx. Even if you try to say, okay, what about choosing u to be x squared, but then du will be 2x dx, and there is nothing you can do about it. You can make it up. Du is not in the problem. You cannot make that x up. You can't do anything here. Not possible. Okay? So it says, use the midpoint rule. We can use the leftmost point, the rightmost point, or the midpoint with 4 subintervals to approximate this integral. So the interval is between 0 and 16. This is what I have. This is what I know so far. And I'll divide it up into 4 equal subintervals. So this is 4, this is 8, and this is 12. So where is the midpoint? Well, of course at 2, at 6, at 10, and at 14. So imagine the function above this interval between 0 and 16. So I need to find the area of the first subinterval, f of 2 times 4 plus f of 6 times 4 plus f of 10 times 4 plus f of 14 times 4. 4 subintervals. Since the base is 4 for all of them, I'm just going to write f of 2 plus f of 6 plus f of 10 plus f of 14. That's all I need.
So you don't want us to plug in
Yes, we have to.
okay.
Yeah, we have to approximate. Well, it's ugly. Oh, I didn't, yeah, I didn't use this over here. Oh, here it is. We were working on conic sections and we didn't get the chance to do anything else. Okay, so 4, parenthesis, e raised to, no, not that. 4 parenthesis, e raised to 4 plus e raised to, what is it, 36 plus e raised to 100. And then plus e raised to 14 squared. Okay, so approximate 5.29 times 10 to the 85th power. Oof. Okay,
It's 5.2 times. Oh, it's
is it okay? Since we're working on this problem, let's work on something from 383, page 383. Please choose whatever you want. Oh, you can't choose because you can't see. So I'd like us to determine some integrals. You choose whatever you want from here, and then we go back to the next question that you would like to work on. So we're given a graph and we're asked to find the integral or approximate whatever. Which one?
33.
Say again.
Is it 33?
Okay, which part you want to determine?
B.
Okay, so we want to work on B. The integral from 0 to, I think it's 5, is it?
Yeah.
From f of x dx, okay? 0 to 5. So I have 1, 2, 3, 4, 5, 6, 7. And then, let's see what will be the best. Yeah. So the best would be to determine this area as a trapezoid, big base plus small base times the height divided by 2, and determine this area as a, so this is 4, 5. Okay, also as, okay, this is x, I'm sorry. So determine this area as a square, base times height divided by 2, and determine this area as a trapezoid. And I'm done. So let's see. So it's this. And this. So base times height, 3. So 2 times 3 divided by 2 plus. Oh. So we chose, what was it, 33 on page 383, and we looked at part B. So the integral from 0 to 5 from f of x dx is the area of a trapezoid. So I started with the triangle. So 2 times 3 divided by 2. And the trapezoid, big base, which is 3, plus small base, which is 1, multiplied by the height, which is 3, divided by 2. So one more time. Big base, 3, plus small base, 1, multiplied by the height of 3, divided by 2. Sorry. So multiplied by 2, divided by 2, and then I also have this piece of 3 by 1. So it's 3 pieces. 3 by 1, okay? I have to make some adjustments. So this base, big base is 3, correct? Small base is 1, correct? But the height is 2. So 3 plus 1 multiplied by 2 divided by 2 plus base, which is 1, times height, which is 3, and then base times height divided by 2 for the area of the triangle. So we determine the area as being, so this is 4 plus 3 plus 3, and that's 10.
Where the other cluster come from?
I'm sorry?
Where the other cluster come from?
You mean this one? Okay, next question. I also would like to go back to one other example that I don't think we looked at. We did look at an area, which was this, because I forgot to erase it, so I always erase it, but I forgot us last time. But I would like us to determine one or the other, so either 14 or 13 or 15. So let's see. Let me zoom in. Okay, speedometer readings for a motorcycle at 12-second intervals. 0 to 12, 12 to 24, 24 to 36, 36 to 48, 48 to 60. Are given in the table. Estimate the distance traveled by the motorcycle during this time period using the velocities at the beginning of the time interval. Give another estimate using the velocities at the end of the time period. Are your estimates part A and B upper or lower? So, any suggestions on this? I'm sure you've seen this in the web assignment. Yes? Which one? Oh, you want to do this? Okay, perfect. So what do we do? Let's copy the table first for everyone to see what we're doing. So here's the table. Time and velocity. So t in seconds, and of course v in feet per second. So this is 0 and 30, and 12 and 28, and 24 and 25, 36 and 22, 48, 24, and 60, and 27. So again, like before with the area, this is what we are determining. The area under the velocity function is the distance. It's the integral of v, which will give us the distance. So the area with the leftmost point, that would be delta x times the sum of f of xi. That's in short. What is delta x? Delta x. Very good. Times. Since we are looking at the leftmost point, f of 0 plus f of 12 plus f of 24 plus f of 36 plus f of 48. And then we'll get a number. How will you write the area with the rightmost point? Exactly. So this is 12, but f of 12 dot 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 plus f of 60. So let's determine this. You'll do the first one, I'll do the second one. Is that okay? So I have 12 times 28 plus 25 plus 22 plus 24 plus 27. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yes. I got 1, 5, 1, 2. Feet. What did you get for the first one? Or I can do 1512 minus 27, but add 30. So I got 1515. Correct me on any of them, of course. So I will say the second one.
For that one.
What is it?
I got 1.48.
48? Because I thought I subtracted 27 and I added 30.
Did you multiply by 12? I think that's what we're going on.
I see, yes. Thank you. Very good. Okay, so then the actual area, which is the actual distance, is not 1512 and is not 1548. But it's the best approximation we can get with 6 subintervals. 5 subintervals with a width of 12 seconds. Very good. Thank you. Okay. Anything else? Next question. Yes, please, Greg.
I'm not sure how we're getting the area to the right.
The area to the right means that this is the first subinterval and I have to start here. If you remember the graphs we looked at last time.
Oh, yeah.
So this is, I just have to start here, and then this is the height here, and this is the height, and this is the height.
Oh, okay.
For the leftmost point, this is the height, this is the height, this is the height for the next one, this is the height for the next one, and this is the height for the last one.
Okay.
So 30 plus 28 plus 25 plus 22 plus 24 will be with the left.
Oh,
But 28 plus 25 plus 22 plus 24 plus 27 will be with the right.
okay, I see. I got you.
Better?
Yep.
Perfect. Good. Next question. I'd like to look at 9 before you choose the next. Okay, I have to keep moving because of my markers are getting. Okay. See, I motivated you somehow. Okay. Perfect. The function f of x satisfies the equation blah blah blah. Find the function.
Can you change the integral from that to f bf of x? No?
I don't even want to. What can I ever be asked to do with that one? Ever. Ever. What could I ever be asked to do with that one? Only one thing.
Yeah. So it's just the same thing I said.
What do we get on the left?
12x plus every,
What do we get on the right?
everything.
That's it. So we determine f of x. Good. Next question. This is it.
Why did it change from f of t to f of x?
Because the fundamental theorem of calculus part 1 says that if a function is given in the form of an integral and you differentiate both sides, when I differentiate, this goes away, but since it's a function of x, this is g prime of x. Better? Good. Next question. If not, I choose.
Number 7,
Number 7, let's take a look.
just like the one.
No. In number 7, we are asked to just show that that's true. The integral from 0 to 1 from x squared sine x dx. They want us to show that it's less than or equal to 1. At this point, we cannot determine this. In the next class we will. It's integration by parts, not a big deal. But in this class we don't know that. So we are not even asked to do that. We're not asked to find this and say it's, I don't know, 1 over 5. And 1 over 5 is less than 1. We're not asked to do that. We're asked to show that the left-hand side is less than or equal to 1. Okay, using the properties of definite integrals. So, where is my starting point with such a problem? Always.
The limits. So from 0 to 1.
Right. That's my starting point. That's all I know. That's all I know at this point. That x must be between 0 and 1. The next step is to try, the next thought I have is to try to build in here what? The whole thing. Right, right. So now remember with cosine. When we looked at cosine in a previous example, cosine was a decreasing function. But what about sine? When we talk about 0 to 1, we mean radians. So between 0 and 1 radian is about 57 degrees. So between 0 and 1, is sine increasing or not? Increasing. Because if it is increasing, when I apply sine to all three sides, left, upper, and the middle, then I keep the same inequality symbol. If the function is not increasing, then I have to switch the inequality symbols, but not for sine. For cosine, yes, cosine is decreasing between 0 and pi over 2. But here, pi over 2 is more than 1. So, but here between 0 and 1, the sine is increasing. Between 0 and pi over 2, sine is increasing. So I can keep the inequality symbol as is. I don't care for the side because the inequality has only 2 sides, not 3. So I can drop that. What should I do next? So I managed to create an inequality or find an inequality that has sine in it, but that's not enough. What do I need to do next? As long as it's a positive number and it's not 0. Well, we're not talking about the limits of integration, right? So it's not 0. So we'll multiply everything by x squared. And then we get x squared sine x less than or equal to x squared sine 1, which is a constant. Okay. I'm happy because I managed to create an inequality. Obviously, the left-hand side is a function lower than the function on the right-hand side. So one function is here, one function is here. Obviously, the area under the first one must be smaller than the area under the second one, right? So I can apply the integral or integrate. Do not forget the x. Do not forget the x, and from 0 to 1. So I obtained what I wanted on the left-hand side. So I have the integral from 0 to 1 from x squared sine x dx less than or equal to. Sine 1 is outside, can wait patiently. What is the integral from x squared? Very good. It is x to the third over 3 from 0 to 1. So the right-hand side is basically sine 1 over 3. Would you agree? My question is this. If you agree that this is less than 1, we're done. Of course it's less than 1. Disregard this number. What is the maximum possible sign that sine can take? What's the maximum value that sine can take? Right, and 1 over 3 is still less than 1. No matter what number is that at the top. But it cannot be more than 1. So 1/3 is definitely less than 1, and you're done. So we show that this is even less than, much smaller than 1. It's smaller than 1 over 3, actually. Let alone smaller than 1.
You plug in 1 from the integral.
Yes,
Take it to the side
yes. So I have to plug in 1 minus when I plug in 0, then
Just 0.
good. Next question.
stop there, or would you keep rewriting to make it write the whole integral again?
Oh, it's good enough.
But then-
Yeah, because this is less than this, which equals this, which is less than that. But yes, you can say, yeah, you can write it again and say the left-hand side is less than or equal to 1. That's fine too. But is the idea clear? Okay. Okay, next question, please.
Number two.
Number 2. Ah, our best friend. Okay, so we have f of x, 2x cubed plus 4x plus 8, and it's a nice interval. Expect the same idea. I'm not going to start the interval at anything else but 0. It's too long. Especially when x is cubed. You don't want to do that, right? So in order to determine the area using the limit of the Riemann sum, what I would do personally, but that's me, I will immediately find the area with the integral to know what to expect. So I'll say the area is the integral from 0 to 4 from 2x cubed plus 4x plus 8 dx. I will do that immediately. 2 x to the 4th over 4 plus 4x squared over 2 plus 8x from 0 to 4. Luckily, I only have to plug in 4. So I have 1/2 4 to the 4th plus 2 times 16 plus 32. Whatever that number is. And as you've noticed, I'm lazy tonight. I need the calculator. So 128 plus 32 plus 30 plus 64. Okay, I got 192. Correct me if I'm wrong, please. So I know what to expect. Quite nice. I don't have to deal with fractions, it appears. So in the calculations. So then I'm ready to write the limit of the Riemann sum. But I need 3 preps. Because the limit of the Riemann sum has so many different pieces in here. I equals 1 through n from delta x f of xi. This is my first step. This is my second step. And this is my third. So first I have to find delta x. Then I have to find xi. And then I have to find f of xi. The better organized I am, the simpler this calculation becomes.
So x is 2 and f of x is 3. So x large.
Oh, the steps. No, this is the step. So step 1, I have to find delta x.
Right.
In step 2, I will find xi.
Oh,
In
x.
step 3, I plug in xi in the function. I can find the function before I find xi, so I can plug it in. So what do you think about delta x? Yes, it's 4 over n indeed. So number 1, delta x is 4 over n. The entire length of the interval is divided up into n subintervals. That's all it means. The width of each base of each rectangle is 4 over n. Is that clear? So we have the interval between 0 and 4. We divide into n pieces, so that every piece has the width of 4 over n. That's the base of the rectangle. Okay, now we want to determine xi. So let me explain again what xi is. So again, the interval is between 0 and 4. This is the first subinterval, second, third, dot, 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 right? So this is delta x, this is delta x. Everything between these bars is delta x. That's the width. So I'm asking myself, where is the generic one? What does the generic one equal to? Well, it equals 0, the end leftmost point, plus I of these. Because x1 will be 0 plus 1 times delta x. x2 will be 0 plus twice delta x, and so on and so forth. So then xi will be 0 plus I delta x. So it's delta x times I, 4I over n. Is that clear? Why are we trying to do this? Remember, because we are trying to determine the limit. And we want to have a representation for all rectangles. And the representation or the area for each and every one of them would be delta x times f of xi for any of these subintervals. For the first one would be this, for the next one would be this, for the third one, but we want a representation for all of them. And then we make I from 1 to n. And then we sum them up, all of them. And n approaches infinity. Is that better?
Yes.
Okay, so and then f of xi will be, I forgot my function. Okay, so it's 2, 4I over n to the third plus 4 times 4I over n and plus 8. So one more time, the area of each subinterval or each rectangle will be delta x, 4 over n, times the value of the function at that point, which is this. That point, and this is the value of the function. Okay, so we have to simplify this into 2. I think this is 64I cubed over n cubed plus 16I over n and plus 8, or 128I cubed over n cubed, 16I over n and plus 8. So these were just the preps. We have not put everything in the limit of the Riemann sum yet. Okay, should I say this again? Do we understand what this is all about? Okay, just one more time. So between 0 and 4, we have a function. This is our function, f of x. And I can determine the area of the first. I can determine the area of the second. But instead, I would like to have a generic interval, which I'm going to consider having xi, the base, which is 4 over n, and the height, which is x of this value, f of xi, from the first subinterval to the nth subinterval. That's what the limit of the Riemann sum is. And the sum will add all these areas from the first to the last, and because n approaches infinity, it will fill up everything. No more gaps, because n approaches infinity. Okay. So now let's write finally the limit of the Riemann sum. The area, limit, n approaches infinity. So from delta x, f of xi, from I equals 1 through n, because I would like us to see if we understand, to not necessarily skip some steps, but cut back on writing a little bit. We know that this is 4 over n, and it does not depend on I. It can go in front. So limit, n approaches infinity, 4 over n. Now, look at f of xi. F of xi, I'm going to write it here, is 128I cubed over n cubed plus 16I over n and plus 8. So I took 4 over n outside because it's a constant. As you remember that 12, right, that we 12, 12, 12, 12 times whatever, 12 times whatever, 12 times whatever. So we took 12 outside. That's the 12 from the previous example with the velocity. So now I have the sum that I need to apply to 3 terms. I can try to cut back on writing by putting the factor in front of the sum of I cubed. Then put the factor in front of the sum of I. And then put 8 in front of the sum of 1. If we don't see this, I will write it out. You tell me. I'll write it and you'll say yay or nay. 128 over n cubed, the sum of I cubed, plus 16 over n, the sum of I, plus 8, the sum of 1, from I equals 1 through n. If this is okay, we'll continue. If you say it's not okay, I'll go back and explain again. Is this clear? Can you see that? Yes, I want to explain it again. So we understand that this piece is made out of 3 pieces, a sum of 3 terms, right? So I have to write the sum of these 3 terms. Instead, I'll write the sum of the first, plus the sum of the second, plus the sum of the third. That's one of the properties of the sigma notation. But also I realize that this is a constant. This is not a constant. It depends on I. So I'll take this and put it in front. And then I take this piece and put it in front. And then I take 8 because it's 8 times 1. So I put 8 in front because these 3 I know. They are from those 4 identities. Better? Yes? Do you want me to write the intermediate step?
No, I got it.
You sure? Okay. So now this gets replaced, and this gets replaced. This one by n, this one by n plus 1 over 2, and this one by n squared, n plus 1 squared over 4. Is this okay?
See, I was gonna ask you about that. Because distribute the 2 instead of breaking
Yes,
them.
but we're not really distributing the summation notation. We are using the property of the summation notation that says the sum of a generic term plus another generic term is the sum of the first generic term plus the sum of the second generic term. We don't really say that we distribute the sigma notation. Is that clear? Do we understand all the steps so far? Yes? Okay, now moving on is just algebra. There is no more calculus till we apply L'Hopital's rule. So we have to simplify this to the max and find the limit. Okay. 128 over n cubed times n squared, n plus 1 squared over 4 plus 16 over n times n plus 1 over 2, and plus 8n. So all I did was to actually replace the sigmas by what they equal to. Now I'm on the hunt for the least common denominator. So if I simplify here, and 16, yes.
Wasn't there an 8 on the second one? Or 16? Yeah, there is.
I'd rather go back and check.
No, it's right.
You sure?
Yeah.
Okay.
I just missed it. It's 16 over n.
Right. So if I simplify the denominator, which I can here, I will never be able to simplify it here. So let's be wise and just simplify n squared with n squared and 4 with 128, but keep n in the denominator because I have no choice. So let's simplify the n squared and just get n. Simplify the 4 and get 32. Simplify the 2 and get 8, but do not change or get rid of n. Because n is still the least common denominator. So what do we have now? I have 32 and I have to expand that, plus I have to distribute 8n to these two, and I have to multiply this because it has denominator 1, I have to multiply it by n. So 32 n squared plus 2n plus 1 plus 8n squared plus 8n plus 8n squared. Is this okay so far?
Is that n squared plus 2n plus 1 or
Which one?
n squared plus 2n plus, right there, yeah.
Yes, because it's n plus 1 squared, 3 terms.
Oh, okay.
Don't make me cry in the pillow.
Yeah, no, I thought it was an I for a second.
Sorry,
The way
sorry.
it shaped.
What? I'm sorry, my apologies. So 8n squared plus 8n and plus 8n squared. We agree with everything. Yes?
You said you didn't take away the ends, that it could be easier.
I could have taken it here, but then I would have had to multiply by n again because the least common denominator must be n.
Okay.
There's nothing I can do with this. If I could have gotten rid of that, I would have gotten rid of this as well.
Okay.
But I can't. Because I have n squared and n cubed, there is no way I can get rid of the denominator. And we will not be able to get rid of the denominator because this is a limit. It has to have same degree over same degree. Otherwise, it's not going to be a number. Okay, ready? For the final step? Yes, it has a lot of steps, if that's what you said. Okay, the denominator now is n squared. 4 can wait outside. It's in the way. I don't want it there. So 32 n squared plus 64n plus 32 plus 16n squared and plus 8n. So now 4, limit, n approaches infinity. 32 plus 16 is still 48, I think. Plus 72n and plus 32 over n squared. I'm done, unless you say you're not, to use L'Hopital's rule. So, okay, it's infinity over infinity. So, fine. 4 limit as n approaches infinity. And this is 96n plus 72 over 2n. And when I differentiate again, I get 96 over 2. So 4 times 96 over 2. If this is not 192, I will have to start from scratch. So how much is 4 times 96 divided by 2? Okay, luckily. Yes.
I thought you just looked at the degrees, so like 48 over 1. So you do 48 times 4.
Yeah.
Right there.
Yeah, but I said, well, in case we don't remember from
Okay.
pre-calculus, that it's the same degree over same degree, so the limit must be 48, leading coefficient over the leading coefficient. Then we observe that it's infinity over infinity, we apply L'Hopital's rule, we get 96 over 2. We apply L'Hopital's rule again, we get 96 over 2, right? 96 and blah, 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 and then multiply by 4. Yes, of course, you don't have to write this. We can already write 4 times 48. Good, that was the limit of the Riemann sum. Next question.